This picks up where the other video left off. This is going to be a little bit of a longer problem. I didn't want to put too much in one video. So here is an interesting question, right? This says find the volume of the pyramid represented by the net. Each triangle is equilateral, and the only measure we're given is that one side of the base is 10. So where do we start this? Well, how do you find the volume of a pyramid? Volume of a pyramid is going to be 1/3 area of the base times height. So the base we already know has a side of 10. So 10 squared is the area of the base. Oh, all right. Here's the challenge. How do I find that height? By height, I mean the height of the pyramid. So if I were to try, emphasize the word try, to draw a pyramid, I would have a square for a base because it tells me that the square is a base. The base is a square. And then I've got this pyramid. And what I need is I need the height that goes from the vertex right down to the middle. So I'm trying to create a right triangle that looks like this, where that's the height of the pyramid. This thing over here is half the length of the base, right? So if the whole base is 10, that thing is 5. All right, so I got that that's 5. And then this thing over here is actually the slant height, right? That's that third side over there. That's the slant height. The problem is I got two variables. How do I solve this problem? Well, if that's the slant height, where is the slant height? Isn't this guy over here actually the slant height? So if I could figure out what that slant height is, that's sort of the key to solving the problem, because once I figure out that slant height, then I can throw them back in that triangle up top, then I can find the height, then I can finish up the formula. So take a look at that triangle, that equilateral triangle, for which I need to find the slant height. If we're told that this side here is 10, then that side there is 10, that side there is 10. So think back a little bit. What do we know about equilateral triangles? Well, we know that each of the angles then are also the same, right? They're all 60. And if I drop this altitude down here, it splits the angles up 30 and 30. And I've formed myself a 30, 60, 90 triangle, and that's the piece that I'm missing. I also know that that altitude is also the median. So if the whole side is 10, it splits it 5 and 5. Well, now look at this. If the short side is 5, then the slant height has got to be short side times the square root of 3. By definition of a 30, 60, 90, there's my slant height. Okay. So now that slant height is 5 square root of 3. Now I can use the Pythagorean theorem to find the missing side. So height squared plus 5 squared equals 5 square root of 3 squared. Okay. So height squared plus 25 equals, when I square this, 5 squared is 25. Square root of 3 squared is 3. So I get height squared plus 25 equals 75. Subtract the 25 from both sides. Height squared is 50. So the height is the square root of 50. If you want, why not simplify this? Right? Remember the simplifying radicals? Square root of 50 can be broken down into square root of 25, square root of 2. Square root of 25 is 5. So my height is 5 square root of 2. All that work to finish up this little piece here. And now I can fill that in as 5 square root of 2. So let's clean up that volume that I have up there. The volume is 1/3 times 100 times 5 square root of 2. So I don't think this simplifies nicely except to write it as 500 square root of 2 over 3 cubic centimeters. And then if you want a decimal approximation, you're more than welcome to throw it in and get a decimal approximation. But that's how you do that. So the only measure you had was that 10 on the side. But knowing that those triangles were equilateral is actually pretty powerful, because then that lets you figure out the slant height, right? That's the altitude of one of those triangles. And then once you figure out the slant height, then you can find the height of the whole object. Drawing in this picture helps too, because now you realize that that's the height. That's the slant height along one of the sides, and that 5 is half the base. The height will always come to the center of the object, assuming it's a right pyramid in this case. So you know that it splits that 10, 5, and 5. Good. All right, volume of a sphere, 4/3 pi r cubed. Simple as that. There's only one dimension in a sphere, and that is the radius, right? There's no base, there's no height. So how big your sphere is simply depends on how big your radius is. The bigger the radius, the bigger the sphere. All right, so the first example says find the volume of a sphere with a radius of 6. So if you want the volume of a sphere with a radius of 6, 4/3 times pi times 6 cubed. Right? What is 6 cubed? 216. So I get 4 times 216 times pi over 3. Does 216 over 3 simplify? It should. Let's see. 216 divided by 3, 72. All right, so now multiply that by 4, 288. I guess I could have done that first. 288 pi, and what are my units? Cubic inches, right? So this is volume. This is how much will fit inside of that sphere. All right, the second one says volume of a sphere with a radius of 5. Well, if I want a radius of 5, I'll do 4/3 times pi times 5 cubed. So this is not going to give me a nice like 288 pi like I got before, because that 5 to the third is 125, doesn't divide evenly by 3. So 125 times 4 is 500. So this will give me 500 pi over 3 cubic inches. Or if I want an approximation, use the pi key on your calculator to come up with an approximation. So do 500 times pi divided by 3. Right? I get 523.60. Right? It's really 598, but that rounds out to a 6. And then I want to indicate that I'm actually accurate to 2 decimal places, so I would put in that 0 to show that level of accuracy. All right, so suppose we want to then compare figures that are similar to each other. All right, so every square is similar to every other square, but obviously they're not all going to be the same size. We had talked a lot about similar triangles in previous units. So what if I look at similar figures? Well, two figures that are similar to each other are going to have linear measures that are in the same scale factor. So if one figure has twice the length of the other, then every side will be twice the length. The scale factor between them will be 2. It could go the other way, right? You could have a rectangle and then a similar rectangle that's half the length on either side. In that case, the scale factor would be a half. So if k is the scale factor, then the areas are going to be a factor of 2 squared, and the volumes are going to be a factor of 2 cubed. So linear area volumes work as k squared, and k cubed. So let's take a look at a little example here. Let's draw a rectangle. Actually, let's draw 2 rectangles, and I'll make them similar. Ratios of the sides are the same. So this one will be a 2 by 5 rectangle, and this one will be a bigger rectangle. All right, so this one will be 6 by 15. Okay, rectangles, and I'm telling you the 2 of these are similar to each other. All right, let's calculate a couple of things. First thing is let's calculate the perimeter. The perimeter of this rectangle is going to be 2 plus 5. That's 2 sides. 2 plus 5, the other 2 sides. So 2 plus 5 is 7. 7 and 7 is 14. So my perimeter, 14. All right, look at this side over here. I've got a 6 and a 15. And another 6 and a 15. So 21 and 21, 42. If you notice, between the 2 and the 6, I'm multiplying by 3. And the same thing with the 5 and the 15. So I claim that my scale factor is 3. Everything on this bigger rectangle will be 3 times the side lengths of the ones on the smaller rectangle. Well, it turns out the perimeter is the same too, right? If I take 14 times 3, you notice that I get 42. So going by lengths, every length on the new one is 3 times the old one. Therefore, the perimeters are also 3 times. It could also work by diagonals, right? Suppose I drew in the diagonal of this rectangle here. Right? Calculate that diagonal, and then calculate the diagonal of this other rectangle. You'll find that the one in the new rectangle is 3 times the one in the old rectangle. So any linear unit for length is related as k. All right, suppose then I wanted to find the area. The area of this rectangle, length times width, 2 times 5 is 10. The area of this rectangle, length times width, 6 times 15 is 90. Well, wait a minute. Now those areas are not 3 times anymore. Now they're what? Now they're 9 times. Why? Because if k is 3, k squared is 9. So if the lengths are related by a factor of k, the areas are related by a factor of k squared. Because you now have 2 dimensions. You're taking length and width. So I've multiplied the one side by 3 and the other side by 3. 3 times 3 is 9. The new area is 9 times the area of the old one. The same thing, by the way, works in 3 dimensions. So let's say, I'm going to draw the whole thing. Let's say I assign this one a height of 4. And because everything's 3 times as big, this one had a height of 12. So now we're talking about a prism. Well, what are the dimensions for the prism going to be? 2 by 5 by 4. So if I want volume, I would multiply 2 times 5 times 4. That would give me a volume of 40. Here, my volume would be 6 times 15 times 12. And that one I'm going to throw in a calculator. Right, 1,080. Well, how do these two volumes relate? Clearly, this one's not just 3 times as big as the other, and is not 9 times as big as the other. Take 1,080 and divide it by 40, and you come up with 27. 27 is k cubed. So if you have 2 objects that are similar, and each of the objects has side lengths that are 3 times as big, then it's going to have 9 times the area and 27 times the volume. Because every time you add another dimension, in this case, you add another factor of 3. All right, so let's go back to these. So now that hopefully this makes a little bit more sense. We got k cubed, and k squared, and k cubed. Length, area, volume. All right, so is it true the viewing area of a 35-inch television screen is about twice the viewing area of a 25-inch television screen? Now, when you measure television screens, you're talking about the diagonal. Well, the diagonal is a linear unit, right? Turns out it doesn't matter what the side lengths are. This thing here is the diagonal, and that's linear. So if I compare the two of them, right, a 35-inch length compared to a 25-inch length, this is the ratio between the two computer screens. So can I simplify it by taking a 5 out of top and bottom? Sure. Make it 7 over 5. So if 7 over 5 is my k, if I want to compare areas, I need k squared. So let's take 7 over 5 and square it. That gives me 49 over 25. Sure enough, that's almost 2, right? It's just shy of 2. It's 1.96. So yeah, almost twice the area. And so if you're comparing television screens, you can do that, right? You could take the two areas, take the two lengths, divide them, and then see what the ratio is. All right, let's take a look at another one. Surface area of a sphere that's got a 10-inch diameter, surface area of a sphere with a 5-inch diameter. Do I need to actually calculate those surface areas? No, I don't. What do I know? I know that the ratio between them is going to be 10 to 5, which is 2. So that is for the diameter. If I want surface area, then I'm going to look at k squared. So if k is 2, k squared is 4. The bigger sphere has 4 times the surface area of the smaller sphere. Right? You could do those calculations. In fact, you're trying to get somebody to believe that. You might try it with a bunch of different measures and have people calculate and realize that every time you do it, you're going to come up with the same ratio, in this case, 4 times as big. Now, how do the volumes compare? Well, if the linear units compare in a ratio of 2 to 1, then volumes are that ratio cubed. So 2 cubed is 8. So in this case, the bigger sphere has 8 times the volume of the smaller sphere. Right, so if the linear is 2, surface area is 4, volume is 8, right? 2 cubed. All right, good. Let's do one more with mass and temperature.